So imagine we have a project. And we measure this project with a series of KPIs, KPI 1 to KPI n, okay? So that we have a multi-dimensional space. I will paint just three dimensions, but you can imagine we can do the same for n dimensions. And the project moves in a trajectory given by this curve, okay? We would like to know if this project is in alignment. Hello? We would like to know if this project is in alignment, meaning that the project curve goes and sticks to one region in space, okay? The space is given by the KPIs, by the normal base of the KPIs given by n KPIs. We want to know if our project is in alignment, meaning that the project moves in time throughout this curve in a certain space that we know. So in this case, within a sphere of radius r. Okay. Let's say that we have the KPIs. KPI 1, KPI 2, KPI 3, and this is the scheduled performance index. This is the course performance index, and this is the timely performance index. Okay. We want to know if our project is in alignment, and we have here, let's say, 80%. We have here 85%. We have here 90%, 91%, 90%. And the KPI number 2 has a cost, a worst performance, 75%, 70%, 63%, 82%, and 78%. The KPI 3 has a timely performance index of 62%, 31 or 32%, 67%, 81%, and 91%. Okay, so you already know what this means. We would like to know if our project is in alignment or not. And in order to do so, we want to reduce our dimensions from 3 dimensions to 2 dimensions, okay? Or from, in general, n dimensions to 2 dimensions or to 3 dimensions. And to do so, we want to know what are the principal components of the project. Okay, the principal components of the project. What this means is that this curve that we have in 3 dimensions is going to be projected in a certain direction, in a new base that is going to give 3 new KPIs: KPI 1 star, KPI 1, KPI 2 star, KPI 3 star. So these 3 new dimensions are going to be those describing the project best. If you want to have this in 2 dimensions, it's easy. Okay, you can have it only in 2 dimensions. Maybe it's easier to understand. KPI 1, KPI 2. We have a cloud of points describing the system. Let's say we only take schedule performance index and cost performance index, and then we want to discover what are the 2 directions that describe best this process, this project. Well, one direction is going to be this. It seems intuitive that this vector describes the ellipse better than the rest, than this vector or this vector. So this is going to be the principal component number 1, describing a lot of variability of the project. This vector is going to be principal component number 2, which is orthogonal to the other principal component. These 2 principal components are going to describe a certain amount of the variability of the system, and this is what we want. We want to describe a certain amount of the variability of the system by finding out which of these 2 vectors, of these 2 directions, are the best for our system. Okay. So in our example, we are going just to take 2 of these dimensions for exemplary reason. We are not going to take 3 dimensions or n dimensions. We are only going to take 2. In case I ask this in the exam, I will only ask it with 2 dimensions. Okay. So the first step, in order to perform a principal component analysis, which is a dimensionality reduction method, the first step is to perform a normalization from a normal distribution towards a normal distribution with mean value 0 and standard deviation 1. How do we do this? It's easy. Mean value, or x, divided by the standard deviation, so x. So what is the mean value? Let's say x is our KPI 1. The mean value, let's say this is x, SPI, and this is y. The third one we don't take, okay? We're only going to take x and y. What is the mean value of x? Well, 0.8 plus 0.85 plus 0.9 plus 0.91 plus 0.90 divided by 1, 2, 3, 4, 5. The standard deviation of x is square root of, I need that value first, all right. Where's my phone? I need that value first, sorry. So 0.8 plus 0.85 plus 0.9 plus 0.91 plus 0.9 divided by 5, 0.87. 2. And then the standard deviation is 0.8 minus 0.872 square plus 0.85 minus 0.872 square plus 0.9 minus 0.872 square plus 0.91 minus 0.872 square plus 0.9 minus 0.872 square divided by 4. Okay? If we do so, well, you can do it, it's easy, okay? The other one, it's the same, 0.75 plus 0.7 plus 0.63 plus 0.82 plus 0.78 divided by 5 gives you that number, and then the standard deviation of 2y. So please perform the calculations. So you have done these numbers, which are easy to do, okay? You just need to go and say, well, I have a KPI star, X star, and I have a KPI Y star, okay? And then I have the number that I had before, 0.8 minus 0.872 divided by this number. Then 0.85 minus 0.872 divided by this number, and so on and so forth. Okay, 0.9 minus 0.872 divided by that number, 0.91 minus 0.872 divided by that number, and 0.9 872 divided by that number. And here is the same, 0.75 minus 0.736 divided by whatever number we have here, 0.70 minus 0.736 divided by that number, and 0.63 minus 0.736 divided by standard deviation, 0.82 minus 736 divided by the standard deviation, and 0.78 minus 736 divided by the standard deviation. Okay, so you have now a distribution that has a value, a mean value of 0 and a standard deviation of 1, and here the same. This is relevant for what we will see in a minute. One moment. Yes?
The transformation from the how many dimensions to the 2 dimensions, can I imagine it like just looking from it, like from the top, and then just measuring?
Yeah, a projection, just a shadow, yeah.
So just the form that it looks like from the top,
yes.
and I compress it
like a shadow, yeah, yes, correct. This is a very powerful method. Where do we